So today we will hear a presentation from our colleague Chang-Gyun Jeong, CJ, on the importance of triaxial sample height to diameter ratio for the purpose of critical state testing of sand. CJ is a senior geotechnical engineer based in our Fredericton office. He has 10 years of experience in various geotechnical projects spanning from playing with dirts and doing tests in the lab all the way to doing fancy, complicated numerical modeling. So with that, I'll pass the floor to CJ.
Thank you. Thank you, Saman, for a great introduction, and thank you, everybody, for the opportunity to share this exciting work. So I'm going to share about the importance of sample height to diameter ratio in triaxial testing, as Saman mentioned, for the critical, especially critical state testings. So I'll give you a historical context first. So critical state testing of silt, sand, and mine tailings has become standard industry practice, as someone mentioned, for assessing the critical state line and stress dilatancy parameters such as North and calibration parameter to better understand the potential for static or so-called flow liquefaction. Conventional use of triaxial specimen with height to diameter aspect ratio of 2:1 stems from work by from back in 1940s Taylor, who found that with 2:1 aspect ratio, the effect of and the friction on peak strength was negligible or minimum. However, the experiment with 2:1 aspect ratio often deform non-uniformity due to bulging at the top or bottom of the sample or sideways bulking. And in dense samples, shear bending leading to wedge-type failure is very common and often limit the usefulness of the test data after a few percent of axial strain, as the critical state void ratio along the shear band is hard to determine. So the work by various researchers in the 60s, for example, Rowe and Bart in 1964, Lee and Seed 67, show that by using oversized end platen and lubricated free ends, a height to diameter ratio of 1:1 result in a stable geometry with much greater uniformity of stress and deformation, leading to towards the multiple failure surfaces rather than one concentrated shear band and general plastic failure. So lubricated, just to give you a context, lubricated free end is the technique to minimize the friction between the soil specimen and the end platen so that sample can freely deform at the end. And this is done by putting a two pineapple-shaped latex membrane with the hole in the center to allow sample drainage and put the grease in between the membrane so they can freely move. And when carrying out the triaxial test to determine critical state, it is apparent that the techniques aimed at introducing uniformity of stress and strain out of ultimate strains of 20 to 30% is highly desirable. But given that the use of lubricated free ends and oversized end platen is recommended by, for example, Mike Jeffries and Ken Bin in 2016, and also featured in a few publications such as UWA round robin critical testing, which was presented to us last year's symposium. But the benefits of 1:1 specimen seem to have remained in academia and have not entered into the commercial practice. For example, as I mentioned, the round robin research on CSL determination, there was about 18 participating labs, and they all used 2:1 specimens. And again, this is more like revisiting the research completed in 60s, but rather than be focused on peak strength like that time, this time our study was focused on the critical state and its interpretation and asking a question like, are they influenced by this aspect ratio difference? So we have completed a series of triaxial tests to investigate height to diameter ratio We have used the GDS automated triaxial machine. As I mentioned, we used the oversized platen 85 millimeter outer diameter for 70 millimeter diameter specimens. And we used the lubricated free end, and the friction is less than 0.5 degree. And to measure the void ratio accurately, we used the end of test freezing method. And all samples were prepared by moist tamping using the slide split mold. So here's an example photo for 1:1 sliding split mold and 2:1 sliding split mold. And sample was all back pressure saturated until it reached a B value larger than 0.98. About 30 triaxials were completed for the research, splitting by half and half undrained and half drained about. So material tested is quartz feldspar glacial fluvial sand, sourced from locally in here, Fredericton, New Brunswick, where the VGC lab is located. We have picked this sand as basically we have infinite supply of this sand here in Fredericton, and we are also working on a few other research projects using the same sand. So that's shape of the particle size distribution, max and minimum void ratio ranges from 0.45 to 0.70. We started with 2:1 test. We did several drained and undrained, prepared to different densities, ensure that different consolidation stresses so that we can reliably determine the critical state line. You can see that CSL is quite curved. I think it's because of the combination effect of compressibility of the grains and also the particle crushing at high stress. And you can see that all loose tests all converge to the unique critical state line pretty nicely. But if you see the dense test here, here, and here, they didn't reach the critical state line. So here's a schematic. If you picture a triaxial specimen for dense subcritical test, it's starting at this initial void ratio, initial volume. But as we load, the sample dilates and number of shear planes are developing within the sample oriented at, say, 45 plus minus 5/2 on the plane of maximum obliquity. But eventually in a dense triaxial sample, especially one has slender height to diameter ratio, such as 2:1, we typically do. Sometimes a single shear plane punches through one side to the other side, and it becomes the dominant shear plane. This is, as you know, so-called shear banding, and it's becoming like two wedges sliding past each other. And at this point, all dilation inside the sample become really, really hard to measure. Within the shear band, you have critical state, but elsewhere in the sample, you don't know what's the void ratio be. However, we can measure the final void ratio accurately after the test, as I mentioned before in previous slides, by freezing the sample and measure the amount of water inside the sample. But this is only gives us the average void ratio over the whole sample at the end of the test and during the test, but not along the critical void ratio along the shear band. And this average void ratio are plotted in red dots here. So that's and this doesn't help us much as it's not the reflection of the true void ratio along the shear plane. And this is a big issue with this critical state dense triaxial test. Okay, now we move on to 1:1 test. We basically repeated 2:1 test with 1:1 height to diameter ratio samples. Loose tests are the same as dense, it all landed on the critical state line. But this time you can see that all dense tests are also reaching the exact same critical state line. And you can see the sample was more uniformly deformed. Similar schematic here. This is similar as before, but those shear plane at 45 plus minus 5 or 2 are not able to pass through and daylighting on either side of the sample. So you end up having a much more uniform sample deformation where the entire sample is engaged and at the critical state void ratio called EC at the end of the test. So question now would be how those two compares. Here's the comparison. When we plot them on top of each other, there's no statistical difference in the critical state line, and they are identical regardless of 1-to-1 or 2-to-1 aspect ratio. And this is good, as now we have learned that there is an improvement in the behavior in terms of we now can use the full test result from both loose side and dense side and you can use it to inform the position of critical state line. But as we know, the critical state line is 3D line which exists in E, P, and Q space. We typically project it to EP as we have seen here, or in a PQ plane. So here's a PQ plane critical state line, similar as EEP plane. This plane is generally used to look at the frictional critical state strength, and I plotted all test results together, similar as before. And as you can see here, critical state line in EP space, critical space in PQ space can be characterized by a single critical state friction ratio of 1.55, which corresponds to the friction angle of 35 degree angle. So the other way to look at this is comparing the behavior difference in various plane. As shown in here. Here shows the volumetric strain versus, I'm not going to go over everything, but this is one important one, volumetric strain versus axial strain, and this is the stress dilatancy plot. Those plot shows the result from the paired dense test, and those two specimens shown here were prepared to the exact same density as you can see here. Void ratio are very close to the third decimal point. But 2-to-1 test, for example, here in volumetric response, 2-to-1 test stopped dilating from about 12% axial strain when it started developing a shear band, whereas 1-to-1 test continued to dilate up to the end of the test up to 30% strain. And you can see the effect in here also up to the maximum dilation, which is a minimum value here. Up to here, 1-to-1 and 2-to-1 doesn't show a very different response. But once you reach the maximum dilation point, 2-to-1 kind of became unstable and came down. Stress ratio came down, whereas the 1-to-1 test result keeps the same stress ratio. And the improved uniformity and definitive point of dilation in 1-to-1 test when compared to the less reliable 2-to-1 test. This is an important observation because this point, the final this point, is often used for interpretation of stress dilatancy parameters for constitutive modeling. And this is another example. This is a dense undrained test with the strong dilative behavior are not conventionally used to define the critical state line. We generally use loose undrained test only to locate the head of the critical state line. But as you can see, you can you were successfully located the critical. It successfully landed on the critical state line. So that's another benefit of using 1-to-1 testing, critical state triaxial test. And an important aspect of the critical state approach is interpretation of dilatancy parameters. And two figures here show stress dilatancy and state dilatancy relationship interpreted using the test result. As you can see, the stress dilatancy can be representative by one set of parameter, which is MTC of 1.55. That's called volumetric coupling, the critical friction angle, and NTC of 0.33. This is called the volumetric coupling parameter. And state dilatancy can be also characterized by a single state dilatancy parameter, regardless of height to diameter ratio, which is chi value of 6.2. As discussed earlier, when comparing the twin test pairings, dilatancy response in the 1-to-1 test was generally very similar to 2-to-1 test for each pairings up to the point of the maximum dilation. However, as again, the 2-to-1 specimen often become unstable near the point because of the development of shear band, and it becomes less reliable. So conclusion, specimens with 1-to-1 deforms more uniformly than 2-to-1, as I showed, and critical state line in E versus low P space are virtually identical. Stress dilatancy and state dilatancy between 1-to-1 and 2-to-1 specimen up to the point maximum dilation are similar, but the 1-to-1 specimen exhibit a more defined point of maximum dilation and continue to dilate towards the critical state after the point. And critical state line can be defined by 1-to-1 testing, loose or dense, drain or undrained, regardless. And height to diameter 1-to-1 testing is advantageous when sample supplies are limited. It's just literally this only need half of the 2-to-1 test volume. And since the need for loose test is reduced, the reliance on moist tamping for sample preparation is also reduced. This is a different topic, but we can prepare the samples using a different various method. And for testing where consistency of result is desired for definition of the critical state and dilatancy parameters, the use of height to diameter 1-to-1 specimen is preferred. And all those work is written down and shared within the community and has been accepted. And this will be published in ASTM Geotechnical Testing Journal soon. And this work has been done with Adrian, Simon, within the team, me, Tava, and Mike, and also other lab staff. Thank you for your attention.
Thank you very much, CJ. Nice piece of work here. There was one question in the Q&A, but I think you answered that. People were interested to see if this work has been published, and I think the answer is in that ASCE journal publication awaiting being published, which is good. I don't see any other question. Oh, just one popped up. There's one question. It's interesting how there is no unique shear band in the 1-to-1 triaxial tests, and there is more uniform deformation at axial strains larger than 10%. Have you thought of writing an addendum to existing standards like the ASTM to address this discrepancy in conventional testing? And can you also comment on how a 1-to-1 triaxial sample can better correlate with in situ undrained strengths recorded in tests such as CPT?
Regarding the ASTM, that's a very good suggestion. Thank you for that. We'll trigger the internal discussion, but I cannot say we are going to do it because that there are other steps to move forward. And for your second question, again, as I said several times, this is we didn't focus much on the peak strength. So if you're saying about the strength conversion between CPT and on-drain peak strength. I haven't had a chance to check those two, and our focus was on critical state strength and about the critical state related testing.
Okay, there are a few questions about the specimen size.
Sure.
Particularly, how large of a specimen have you tested for this 1-to-1 aspect ratio?
For this work, we only used the typical standard size triaxial. So diameter is 7 centimeter and 2-to-1 for 2-to-1 test. So it's a 14 centimeter high, 7 centimeter diameter, and for 1-to-1 it's a 7 and 7. And I haven't had a chance to try with the other larger size samples.
Okay, there are a few other questions in the chat, but I think we're getting to the top of the allotted time. I'll just maybe pose one of them. Are there any plans to extend this work for cyclic loading?
That's a pretty good idea. I can I can internally discuss. We didn't plan to do it yet.